Okay, guys, in this example, we have a charged disk, very thin disk, and we put a positive charge on the surface and homogeneously distributed. So we would like to find out what's the electric field just a distance z above the center line of this shape. We know that the electric field will be totally in z direction because of the symmetry. But now, unlike the one-dimensional problem, we need a two-dimensional shape such that when we integrate, it covers the whole region. And the only obvious solution for this is just using the ring, okay? And besides, we know the electric field due to the ring, but the thickness of the ring will be dr, and the distance from the center will be measured as small r, and the capital R is just the total radius of the disk. So R will be changed from 0 to R during the integration. So this is what we will do. But dE, which is this, okay, dE will be given by this expression, okay. However, remember that this is the ring. This is due to ring. Okay, Kz or dq over r prime square. R prime is the distance from this dq, because inside this stripe there is dq, and the distance from here is given by this distance, but it's z square plus r square from geometry. Okay, so this is z, this is r, and this is r prime. So r prime square should be there. So the result is just simply k times z dq divided by, okay, z square plus r square square root. Okay, no, r square, this to the power of 3/2, and this is 3/2, right? 3/2. This was the expression due to the ring that we found earlier. Okay, and we are using the same thing. Instead, in previous case, we had z, instead of z we had x, but instead of okay, yeah, just this was the only difference. Okay, instead of x we are using now z. Okay, so this is the expression due to the ring as before, and also for this r we have to use small r. Remember earlier we used a here, and it was the radius of the ring, but now radius of the ring is just r. That's why we have now r squared there. Okay, so this is the only difference. But now again we have to go dq to d something, d theta. Usually we learn that we can go d theta or d r or something like that. I think this choice is much better. The reason is this, okay? Now, because this is two-dimensional case, we use a new definition, which is called sigma. Sigma is the surface charge density. Earlier, we used linear charge density, but now we are using surface charge density, and it's the charge, okay, divided by the area, differential area. The small charge within the small area. Of course, the area is this one. Or the total charge divided by the total area. Now, the total charge is Q, and total area for this shape is just pi capital R squared. But what about this dA? Now, if you look at this stripe, okay, this stripe, okay, the radius is R and the thickness is dr, don't forget. If you cut from here, cut and open, as you see, this shape will be like that. Maybe the edges will be a little bit bent, you know, but because the thickness is very small, dr is very small, so that this is almost rectangular in shape. So, but this side will be just dr, but this long side will be just 2 pi r, which is the circumference of this circle, where inner distance and outer distance are almost the same because dr is very small. In this case, the area of this rectangular segment is just nothing but the product of these two, right? dA will be given as 2 pi r dr. Now here, how we can go from dq to dr by using this expression. So from this, dq will be given as sigma times 2 pi r dr. Okay, dq will be given by this, right? dA is given by this expression. Okay, so since everything is given, then we can put everything together, and then we can now write everything. Okay, so that the electric field will be given by Z sigma divided by 2 epsilon 0. Okay, integral now. As you see, R changes from 0 to R. So if you put everything together here, okay, instead of dq, we write this, and then z is there, and these expressions are already there. This is what we are having now. R times dr divided by, okay, z square plus r square to the power of 3/2. So this is an R integration, which is not difficult to handle. Okay. Arkadaşlar, şeyi kapatın mikrofonu lütfen. There is a little bit noise with the microphone. Okay, anyway, so how can we integrate this? Very simple, because now since we can use the change of variable, we say that u equals z square plus r square, and du will be equal to just 2r dr in this case, okay? And z will not have any contribution because z is constant. As you see, it's the distance at which the electric field is measured. That's why it's constant, and the derivative of r square is just 2r times dr. So instead of r dr, we can use du over 2. So r dr will be equal to du over 2, and then this will be u to the power of 3/2. So the electric field will be given by z sigma divided by 2 epsilon 0, okay? And then instead of dr, we have now 2 du over 2, okay? Here, du over 2 divided by u to the power of 3/2. Okay. Okay. Now, if you put everything together, what we end up with is that the integral of okay, u minus 3/2 du is nothing but minus 1 over 2 u to the minus 1/2. Because when you take the derivative of this, sorry, not minus 1 over 2, but it's just minus 2. When you take the derivative of this expression, okay, the derivative of u to the minus 1/2 is just put this in the front, so minus signs and 2's will cancel, and u to the minus 1/2, because you subtract 1 from the exponent. This is how you get the derivative of the exponential terms. So basically, this is the result for this one, okay? When you insert everything and convert u into z square plus r square, this is exactly what you will have. Z sigma over 2 epsilon 0, okay? Z sigma over 2 epsilon 0 times, okay, times minus 1 over u to the power of 1/2, or square root of u, but u is given by this expression. So square root of z square plus r square. Now r is changing from 0 to capital R, okay? So if you put this in, okay, so you will have z sigma over 2 epsilon 0, okay, if you put the upper limit, minus 1 over square root of z square plus capital R square, but when you put 0 for this, it's just plus 1 over z. Why plus? Because the lower limit is minus, and there is another minus, minus gave you plus. So now if you put this z inside, multiplying these two terms, you see that it's sigma over 2 epsilon 0, okay, times 1 minus z over square root of z square plus r square. So this is the result. So this is the electric field in z direction for the disk, So now what happened? When z is very small, this term is negligible. When z is much smaller than r, then z square is even smaller, way smaller than r square. So it can be neglected. So that square root of r square gives you r, which is a finite number, and the denominator is not 0, so the expression didn't blow up. But since z is extremely smaller than r, so this will be a very small number divided by r, but this is also very small. So in this case, you can eliminate this, and you see that for z very small, okay, small z, in other words, very near surface, electric field will be given as sigma over 2 epsilon 0. This is a really very interesting example, because we will use this result very often, okay, in considering the charges and also the capacitors and everything are explained by using this thing. So this example is very important. So please pay attention how it's obtained. So for very small distances, you see what we have is that. But for very large distances, when z is much greater than r, it means that in this case, I can cancel this one comparing with this one. So square root of z squared gives you z, z over z is 1, but 1 minus 1 gives you 0. So as you see, electric field goes to 0 when you are so far away from the surface. This is good, because this is physically expected. Okay, we expect to get 0 or very small and smaller electric field when you are away from the shape, whatever the charge distribution is given. Okay, whatever the shape it is, because you cannot distinguish what kind of shape it is. Remember that earlier for the ring problem, I told you that when you are so far away, you cannot really distinguish if this is a point charge or just a ring, okay, because it's too far away. So the electric field should always be reducing when you are getting away from the source, whatever the source is, of course. So this is the end of this recording. And now I will again ask you if you happen to have any questions.